Analytical formulation. The aim of the micromechanical approaches was to determine the equivalent elastic constants of composite material considering individual elastic constants constituting the composite material. The equivalent elastic constants, E1, E2, G12, Nu12, of the fiber reinforced composite have been determined analytically in terms of the relative volume fractions, Vf, Vm, and elastic constants, F, M, Gf, Gm, Nu-F, Nu-M, of fiber and matrix. It may be mentioned two basic analytical approaches in micromechanics of continuous fiber matrix composite materials in obtaining the equivalent elastic constants. The first one was the rule of mixtures, ROM, and the second one was the Halpern-Tsai semi-empirical model. The first model rule of mixtures defined as the mathematical expressions that give the elastic properties of the continuous fiber composite material in terms of original material properties, volume fiber fraction, and arrangement of its constituents, A, the apparent Young's modulus in the same direction as the fibers, E1, 2, B, the apparent Young's modulus in the direction perpendicular to the fibers, E2, 3, C, the major Poisson's ratio, Nu12, 4, and, D, the in-plane shear modulus, G12, of a lamina. 5. Rule of mixtures, ROM, equations have been listed and shown as the formulas below. The second model Halpern-Tsai included the expressions obtained by curve fitting as, A, the apparent Young's modulus in the same direction as the fibers, E1. 6, B, the apparent Young's modulus in the direction perpendicular to the fibers, E2. 7, C, the major Poisson's ratio, Nu12. 8, and, D, the in-plane shear modulus, G12. 9, of a single layer of layered composite ply. These related equations have been listed and shown below. The reinforcing factor, Xi, measuring reinforcement of the composite, is variable depending on the fiber geometry, packing geometry, and loading condition. It is a measure of reinforcement of the composite. The values of Xi have been obtained by comparing the EX 7 and 8 with exact elasticity solutions, and corresponding curve fitting results. The generalized Hooke's law equation is as follows. In this equation, sigma I is the stress vector, sig is the stiffness matrix, and epsilon I is the strain vector components. In functional form, sig has been represented by 11, in terms of the elastic properties of the fiber, matrix, relative volume fractions of fiber and matrix. In most literature studies, the basic analytical approaches have been presented without taking into account the adhesion of the interface across the end faces of the fibers and the stress concentration effects at the fiber ends.